How can we improve the latency of a Python service by using Rust, writing the Rust code, and compiling it to a library, and then importing it into Python? Turns out we can totally do this. It's actually really possible. There's a lot of different ways to go about it. And this was a question that was originally asked by Full Outer Join. I love that name. It's a great name. The idea is we can make some improvements, maybe not by going to 100% Rust, but still using Python at the top level that can access low-level Rust. Now, it's totally possible. So we can do this. One of my favorite approach, obviously, we can go into Python extensions, CFFI bindings, PyO3 will do this for you a lot more easily. That's the idea, is that you can create your Rust code, write your Rust code, and then compile it for native Python extensions. So you can import it as a module directly in Python. So they make it really easy. I mean, you just sort of annotate your function that you're going to be exporting, right? And then you just run Maturin. Maturin? I think Maturin. Then you import your module, and then you can access the functions directly. Super easy. All right, we have another question here. What are the Rust crates, or sort of like the modules, the Rust modules, right? Rust crates that we could use to import into our Rust application that leverage directly the idea of ingestion and data pipeline. We want to be able to leverage that technology. What are the best crates for this? We've got a couple of ideas. Really depends on what you're going after. I mean, it's all about kind of what really systems that you have up and running, what kind of architecture. Using Kafka, are using other kinds of brokerless technologies, are using a message bus or a queue. There's a lot of ways to go about it. So you always want to take into consideration just a handful of libraries that work really well in tandem together. Anything that supports Tokio. So Tokio is going to be the primary asynchronous library that is used inside of Rust applications. There are a lot of other approaches and other alternative libraries that have different performance considerations. Tokio is really good because it kind of became the standard. Many years as Rust has been out, Tokio has been out, just essentially came out near the beginning. And so it's evolved, it's had performance improvements. Tokio is going to be great. And all these libraries here together that I'm talking about all support Tokio as the asynchronous I/O. So if we're looking at making HTTP calls, maybe that's the way that you're going to emit events, right? So Reqwest is the standard HTTP client. You also have Hyper, which is typically a lower level library that you could use, and Reqwest usually wraps around Hyper. Then you got Axum, which is a web server. It's my favorite web server because it provides a lot of great capabilities. RD Kafka is for Apache Kafka. Nats is another one. And then your serializer. How can reducing data ingestion from 120 milliseconds down to 30 milliseconds really be meaningful to a user's experience? Because I mean, to think about it, human perception, it's kind of hard to perceive that 90 milliseconds because it's not a lot. That's a very quick time. Like a lot of milliseconds go by very quickly. And humans, we can't really perceive that. Well, from our perspective, we typically call our users the developers, right? The developers are using our APIs, and they want our APIs to work well together. If we have an API that sends data, we also want an API that can read the history of the data that was sent previously. And if those two are, asynchronous, the latency difference is going to be meaningful from an impact. So for example, we've got developers sending and receiving data on mobile apps and web apps to do things like multiplayer games and chat experiences, the dot that's moving around on the map where your car is, and things like that. So those kinds of experiences are latency sensitive. You really see latency come into perspective when it's a real-time experience. And so latency is really critical from us from that perspective. Also, it's kind of usually when our customers, right, our users, our developers, they come to us and they have, hey, I'm seeing a problem here. I notice a problem. I make an API call to write data, but then I read the data and it's not there. Well, usually we say, okay, we'll just put a sleep in. That's kind of a hack. You don't want to have to do that. And it's just sort of bad practice in general. So the more we can reduce the need to do that, the better the end user experience is, and developers are the API users in our system. So we got a question here from PJMLP saying, as much as it's fun to sort of demote the idea of using C for modern applications and preferring programming languages like modern Rust, we have seen that in the years, the experience of using C in distributed Unix apps and games, including game engines, right, where C is a huge part of that, It's the approach that we took to improve some latency by migrating a Python app over to Rust is largely architectural and potentially with some knowledge gaps. And yeah, that's pretty much the case. So we could have done this whole project in C or another language, or have improved our architecture in a rewrite using Python to get similar gains. With our experience in C and Rust, we wanted to take the most advantage. Because it's a full rewrite to migrate a Python application to a new way, a new architecture to gain a lot of performance benefits, Rust was the best choice for us because we are getting really good at it. Every time we deploy a new Rust application, we see significant benefits, and all the safeties that are built in, like the concurrency safety, which is a big one, and memory safety, which a lot of other languages have as well. That concurrency safety that Rust brings along with it is really powerful, and we get to net all the benefits and performance of C code, which we are really familiar with C code because our message bus, our core message bus, it's written in C today, this very moment, and our message bus connects 1 billion devices that process 3 trillion JSON messages every month, which is 25 petabytes of JSON data. That's a lot of data. And we could not have achieved this without C in our message bus and asynchronous I/O with some added considerations on assembly optimizations. When we're making improvements to a Python application to improve its performance, there are a lot of options that you can take, including some non-coding options like changing the runtime. So CPython is the standard distribution of Python that comes with all your systems today. CPython will be installed by default. Even if you install Python with a package management system like apt or yum, you're going to get CPython. There are other runtimes though, including runtimes like PyPy and Jython. Oh, and stackless Python too. So all these different options will have better performance considerations when you're dealing with the standard CPython. Jumping over to PyPy, for example, gives you usually about 4x performance boost. There is a takeaway though with PyPy. We do use PyPy, and it costs a significant amount of RAM. You're going to get RAM that would normally be running at maybe 200 megabytes or maybe less on a normal Python process, and it's going to be replaced by gigabytes of Python. And that's a lot of Python to be having memory consumed on your system. Gigabytes, though you do get a nice performance benefit. So if you can trade off compute for RAM, it's going to be worth your while. When you're charting metrics, you want to sort of chart a variety of different views on that data, because different aspects of the data, even though it's the same metric, will have implications. For example, are you doing the median, the average, the mean, right? Or are you looking at percentiles? And they're all important. Now, chart A here, let's take a quick look at what chart A is on our chart. Here's chart A, the end-to-end write latency. Now this is showing average. I like average because it's going to show you a full picture. Even though it's smoothed in some cases, it's going to show you a picture of what you should pay attention to. Because if you see like little spikes here and there, you can then zoom in and look on the 99th and see if it's just a one-off that's a significant outlier, or if it's a bigger deal, maybe past the 50th percentile. And we calculate that chart A as an average with the sum of all the latency metric units over the count over a minute, which is the window of our bucket, and then we can chart a dot on the graph based on the latency for that minute. The average is my favorite because it does show you a sort of an overall picture. It can any of these percentiles will show you they'll show up usually in the average as a skew on the average chart. That means you can jump in and check to see how many users are actually affected by this. Is it one user at the very end, that one slowest user that has the worst case scenario? And then we can look and see what's causing that. Or is it a larger population of the users? We can see that. And why I like average is it sort of covers the full picture.